In this lecture, I'm going to discuss the property that distinguishes Q and R. So just to recap, last time we talked about Q and R being ordered fields. So both satisfy the same set of properties from a point of view of arithmetic operations, addition and multiplication. So the distinction that we have seen so far was in the fact that algebraic numbers, not all algebraic numbers are included in Q, and if we express all rational numbers in a decimal form, so that they become terminating or repeating decimals, then, and we plot these numbers on a number line, then the number line will have whole corresponding to non-terminating, non-repeating decimals. If we include those, then we saw that those holes are going to be removed. So now I'm going to look at the same property, but from a somewhat a different point of view. So just like before, let me denote by V a set of all rational numbers or all real numbers, because at this point I'm going to discuss things that are applicable to both sets. So if V is Q or R, then we're going to give several definitions. So definition number one, if we have a number that belongs to V, so that means that capital M is either rational or real number depending on the context, then we're going to call this capital M an upper bound for some set S, capital S, and V. So capital M is going to be an upper bound provided that for any element of a set S, for any number in a set capital S, that number is going to be less or equal to M, to capital M. So in that case, we're going to say that capital M is an upper bound. Likewise, symmetric to this, little m in the set V is a lower bound for the set capital S, provided that S is greater than this lowercase m for every S in capital S. Now, one thing that I want you to understand is that these upper and lower bounds are not unique. For instance, if 1 is an upper bound for the set capital S, and certainly 2 is an upper bound if everybody is less than 1 in my set, then likewise everybody is less than 2, less than 3, less than 2.71. So once there is one upper bound, then there are infinitely many more, right? Any number be above my upper bound is still an upper bound. And likewise, if let's say 0.3 is a lower bound on my set, then any number below 0.3 is also a lower bound. If all numbers in my set are going to be bigger than 0.3, then they're certainly all positive, so they're all greater than 0, they're all greater than -1, and so on. Okay, so let's give a couple of examples of for these concepts. Let's say we're talking about the set capital V, which is a set of all reals. And as a set S, I'm going to choose what is called a finite set, a set that contains finitely many elements. In this case, it would be just 3 numbers, 1, 2, and 3. Then clearly, this set is going to be bounded from above because the largest element here is 3. So 3, in fact, itself is an upper bound because everybody in my set is less or equal than 3. 4 is an upper bound, pi is an upper bound, 17.63 is an upper bound, etc. And in a similar way, the smallest number in the set is 1. So then 1 or anything below it is going to be a lower bound. So in particular, 0 is a lower bound, any negative number is a lower bound, etc. Example number 2, still I'm going to consider a set of all real numbers. I take a subset, which is a half-open interval from 0 to 1. Remember that half-open interval means that I'm taking all numbers between 0 and 1, not including 0. So then again, the largest number here is 1. So anything bigger than 1 is an upper bound. 1, 200, 1,012, and so on. All numbers in this interval, half-open interval, are greater than 0. So then 0 is an example of a lower bound. Minus 0.1, minus 53, all of those are lower bounds. Still, I'm going to take v equal to r, so I'm working in a set of real numbers. And let's take a set capital S, which includes all real x, such that x squared is between 0 and 2, not including 2. Well, then this actually means that I'm looking at an interval from 0 to square root of 2, right? If x squared is between 0 and 2, then x is between 0 and square root of 2. It is greater or equal than 0 and strictly less than square root of 2. So that's again an example of a half-open interval, except that the right-hand point is, which is square root of 2, the right-hand point is not included. Well, then any number which is equal to square root of 2 or bigger is an upper bound because it dominates all terms, all numbers in capital S. And any non-positive number is an example of a lower bound. So 0 is a lower bound, minus 6 is a lower bound, minus 2053 is a lower bound, and so on. All right. Next example, number 4. I'm going to do exactly the same thing. I'm going to say, take a set, V now, which is a set of rational numbers, and I'm going to specify S in the same way. It would be a set of all rational numbers, squares of which are between 0 and 2, not including 2. So notice my new definition of S, because now S is just rationals. So it does not include all S's, all X's from the previous definition of S here. So this set is strictly smaller than a set S before. Okay, but it's still, there are still upper bounds, because if I take any rational number, the square of which is greater than 2, then that's an upper bound. So if I take 2, right, then 2 squared is equal to 4, 4 is bigger than 2, so x equal to 2 would be an upper bound on this set. X equal to 3 is an upper bound, x equal to 1000 is an upper bound. But notice that square root of 2 now is not an upper bound anymore, because square root of 2 is not a rational number, as we proved, so it cannot be an upper bound in Q, because square root of 2 does not belong to the set of all rational numbers. Now, just like before, any rational number which is less or equal than 0 must be a lower bound. Okay, the last example here, let's say I still take my set V as being a set of all rationals, and as a subset of it, as a set in V, I'm going to take a set of all natural numbers, so all positive integers. And then it's easy to convince yourself that if I take any rational number which is less or equal than 1, then that rational number is going to be a lower bound on n, because any rational number below 1 is less than any positive integer. And there is no upper bound here, because if I choose any capital M, and I claim that that capital M is bigger than any natural number, then certainly I would fail, because I can always find a natural number which is bigger than any prescribed number. So in this case, there is no upper bound. Okay, so then we give another set of definitions, which are closely related to what we just did. If I have a set S in my space V, that set is going to be bounded from above if there is an upper bound for capital S. a set is bounded from below if it has a lower bound, and a set is just bounded if it is bounded both from above and below. So if I have a set S and there is a number which dominates all numbers in S and another number which is below any number in S, then it means my set is just straightforward bounded. So if we look back at the example set we just considered, take a set space V equal to R, all real numbers, consider a set 1, 2, 3 that belongs to that set. Then clearly there's an upper bound 3, lower bound 1, as we discussed, so the set is bounded from above, bounded from below, so then it is bounded just by itself. Second example, if I take still V in R equal to R, S is between 0 and 1. Again, we had an upper bound, which is any number greater or equal to 1. Lower bound, any number greater or equal to 0. So bounded from above and below, that means bounded. In the third case, again, we're bounded because x is between 0 and square root of 2. So that means that we have both lower and upper bound. In the fourth case, same thing. Again, x is going to consist of all rational squares of which are between 0 and 2. So 0 is a lower bound. For example, 2, x equal to 2 is an upper bound. So therefore, this set is bounded. And then the last example where we have all natural numbers, we consider all natural numbers in a set of rational numbers, and that set is, we should write this here, it's bounded from below, right? Because 0, for example, 0 is a lower bound, but it's not bounded from above, so therefore it's not bounded. So once again, S equal to n is bounded from below, but it's not bounded overall because it's not bounded from above. Okay, the next set of definitions, again, fairly intuitive. Still, if I have some subset of my set V, where V is either rationals or reals, then an element of the set S is going to be a maximum of S if this element is also an upper bound. So that means that an element S is a maximum if it belongs to the set, and it also dominates all other elements in the set, right? Because that's what it means to be an upper bound, so we will denote this by max of S. Again, you can give a symmetric definition. If you have an element which is also an element of your set, which is also a lower bound, then it is called a minimum and denoted by minimum of S. Once again, we'll look at the same examples as before. If I take a set of that consists of just 1, 2, and 3, then clearly 1 is a minimum, maximum is 3. And in principle, something to realize that whenever I have a set of finitely many numbers, then there is always a largest number, always a smallest number. So any finite set will always have a maximum element and a minimum element. That's not going to be true for infinite sets. So for example, in number 2, S is between 0 and 1, not including 0. So that means that 1, which is an upper bound, is also an element of a set, so a maximum must be equal to 1. 0 is somehow the greatest lower bound here, but 0 does not belong to the set, so the set does not have a minimum. Similar for this guy, if these are, and we define S as x squared between 0 and 2, not including 2, so then maximum does not exist, because maximum would have been square root of 2 should it be included, but it's not. And the smallest element is 0, so minimum is 0. Similar to this, if I do exactly the same thing, but now I'm sitting in a set of all rationals, then just like in the previous case, this set is not going to have a maximum because 0 is not included, but it would have a minimum which is equal to 0. And then in addition to that, so if we take now our last example of a set of all natural numbers or all counting numbers, then the smallest here is 1, and there is no larger, so no maximum, but there is a minimum which is equal to 1. And let me actually give you one more example here. Let's move this down. Okay, so no maximum minimum of s is 1. Let's consider a similar situation to 4, but I'm going to interchange the inequalities. So s is going to consider of all rational numbers such that 0 is less than x squared less or equal than 2. Okay, so in this case, the smallest number would have been 0, but 0 is not an element of a set, so there is no smallest element of the set, so no minimum of s, but certainly there are lower bounds, right? Because 0 is not a minimum, but it is a lower bound, because 0 is below all terms in s. Well, and now what about the maximum? So the maximum of s would be square root of 2, but clearly square root of 2 is not available in Q, so no max of s either. Right, so in this case, s does not have either a minimum or a maximum, even though we defined this as x squared less or equal than 2, but including equality is meaningless because x squared cannot be equal to 2. Okay, and then the last two definitions that we will need to know are going to be the following. So let's say I have a set. That set has an upper bound. Then I already said that if I choose any number larger than this upper bound, then that is going to be an upper bound too. How about if I choose a smaller number? Can I guarantee that is an upper bound? Well, clearly not. But I should be able to, if there are upper bounds, I should be able to, in principle, find the most efficient upper bound, an upper bound which is smaller than all other possible upper bounds. So this is going to be something that we will call a special name. The least upper bound for the set S, if it exists, is going to be called the supremum of the set capital S, and it's going to be denoted by this sup of S. And then I can do the similar thing for lower bounds. If my set is bounded from below, it has a lower bound, then any number below the lower bound is still a lower bound, but any number above the lower bound may or may not be a lower bound. So then we consider the greatest lower bound, if it exists, for S, and we call that the infimum of S. So let's look at those again for our set of examples. So example 1 again was V is R. So I'm working in a set of all reals. And S is a finite set, 1, 2, 3. So what is the smallest upper bound for S? We're going to consider proving that something is an upper bound or lower bound shortly, but for now I'm just giving you examples. So clearly, in this case, the smallest possible upper bound is going to be 3. Right, so supremum of S is 3, and the least, so the least upper bound is 3, that's a supremum. And then the greatest lower bound, here any number less or equal than 1 is a lower bound. So that means that if you have any number less or equal than 1 as a lower bound, and in fact, anything above 1 cannot be a lower bound because it's not a number less than 1. So then the infimum of S must be 1. Number 2. So let's do this guy. So this set, we said, satisfied the following property, that the maximum here exists and is equal to 1, and a minimum does not exist because minimum would be 0, but 0 is not included in the set. So there was a maximum but no minimum. So what about the supremum of S? What's the least upper bound? Well, any number bigger than 1 is an upper bound. In fact, 1 itself is also an upper bound. So the supremum of S, and that's the smallest upper bound, right? I cannot go lower. So supremum of S is equal to 1. And then how about infimum of S? Well, so in this case, again, any number less or equal than 0 is a lower bound. So the greatest out of those is 0, so infimum of S must be 0. So maximum existed, minimum did not. But supremum and infimum both exist, right? So infimum, in a sense, is not a minimum, but it's almost a minimum, because infimum is somehow the smallest number that you can reach, but if that number is not in your set, then there is no minimum. Number 3. So let's see what happens to number 3. So here we had minimum 0 and no maximum, because the maximum is when x squared equal to 2, but 2 is not included. Well, any number which is less than 0 is going to be a lower bound. So the largest lower bound, or infimum of S, that must be 0. And what about the supremum of S? Well, in this case, anything which has any number which has a square greater or equal to 2 is going to dominate all terms in capital S. So then the smallest out of those is going to be x squared equal to 2. So the least upper bound should be square root of 2, right? Because that's the smallest number which is greater than everybody in the set. Example number 4. Similar thing, but now in a set of rationals. So is there any difference? Well, what are lower bounds here? Lower bound is anything which is less or equal than 0. The greatest, any rational number less or equal than 0, the greatest rational number out of those is 0 itself. So again, infimum of S is 0. And what about the supremum of S? Well, once again, if I would have been in a set of all reals, then the smallest number, which is larger than anything in my set, is going to be square root of 2. But in this case, square root of 2 is not included. And so that means that because square root of 2 is not an element of V, it's not a rational number, so then supremum of S does not exist. We're going to prove this in a moment. So number 5, V is still Q, and S is a set of all natural numbers. So in this case, what is the infimum of S. Any number less or equal than 1 was a lower bound. Greatest out of those is 1. 1 belongs to Q. It's a rational number. So infimum is 1. And then supremum of S, well, there are no upper bounds here at all. So the least upper bound does not exist. So does not exist. Okay, so I hope that with these examples, it is clear to you how this works. So now let's see how we can prove, for example, let's think about numbers 3 and 4 possibly. So first of all, let's write down the something. Let's write down the following thing. Let's say I'm going to suppose that S is a supremum, let's make it S0, is a supremum of capital S. Well, what does it mean? It means that number 1, S0 is an upper bound on S, and number 2, S0 is the least upper bound on S. Well, what would be the statement equivalent? What does this mean actually? Okay, S0 being an upper bound on S means that S is less or equal than S0, right, than my upper bound, for every S in capital S, right? It just means that S0 is an upper bound. And then number 2, I have to specify for what it means for us not to be, for what does it mean for us to be the least upper bound? Okay, so what does it mean for us to be least upper bound? It means that if we consider any, any t which is less than S0. What does it mean that S0 is the least upper bound? So that means that then t is not an upper bound on my set capital S, right? So if S0 is the least upper bound, then any number below S0 is not an upper bound for S. And what does that mean? For any t which is less than S, because it's not an upper bound, that means that I should always be able to find less than 0. The fact that t is not an upper bound means that I should always be able to find an element of my set capital S which is greater than t. So there exists an S in capital S such that S is greater than or equal than t. Right, so once again, what does it mean that S0 is the least upper bound? It means that if I go below 0 and I consider some number t below S0, then that's not an upper bound, and that means that I should be able to find an element which is larger, in fact, strictly larger than t. So therefore, to test if S0, so to test whether S0 is a supremum of S, I need to check two things. So let me reorganize this a little bit. Check 1. S is less or equal than S0 for all S in S. So you're verifying that S0 is actually an upper bound. And number 2, show that for any t less than S0, there exists an S in S such that S is greater than t. Right, so part 1 again implies that what you have is an upper bound. Part 2 implies that this upper bound actually is the least upper bound. And we can derive the similar condition for the infimum. And I'm just going to list it to test whether S0 is an infimum of S. We have to verify again the set of symmetric assumptions. Infimum means that it's a lower bound. So a lower bound says that it's a number which is less than all elements of your set. So S should be greater or equal than S0. So that means that S0 is a lower bound. And what does it mean that S0 is the greatest lower bound? It means that if I go slightly above S0, then what I got is no longer a lower bound. So that means that I should be able to find an element below that element which is higher, above that number which is higher than S0. So if we pick any t greater than S0, S0 is the greatest lower bound, so then t is not a lower bound, and so there must exist some S, some element of your set, which is less than t, right? Because t cannot be the lower bound, so I can find at least one element which is going to be smaller than t. Okay, so then let's do yet another example. Let's say I want to show that if V is R and S is that same set that we considered before, X is in, let's say, in R, is such that 0 is less or equal x squared less than 2. So I want to show that then the supremum of S is equal to square root of 2. So proof. What do I need to verify? I need to verify these two conditions, right? That number 1, square root of 2 is an upper bound, and number 2, that it is a least upper bound. So number 1, if my set is defined, so from the definition of S, if X is an element of S, then X squared is less than 2. And solving this inequality, we have that x must be less than square root of 2. Right, so therefore, condition 1, that all elements of my set must be less or equal than square root of 2 is satisfied. So the conclusion that I can draw from this again is that square root of 2 is an upper bound on S. And now I need to check if there's a least upper bound. So number 2, I'm going to choose any t. So if it is a least upper bound, and if I go slightly lower than square root of 2, then the outcome is not an upper bound. So I'm going to choose any t which is less than radical of 2. And now I need to show that there exists an element of my set which is greater than t, and that would be enough to conclude that t is not an upper bound. Okay, so then if t is less than square root of 2, and then if I take t, actually if I take this inequality and I add square root of 2 to both sides, right? So then t plus square root of 2 is going to be less than square root of 2 plus square root of 2. This comes from the same properties of ordering that we discussed before, right? So if I have number is less than another number, if I add the same number to both sides, then the inequality holds true, right? So this is from the properties that we proved in the previous section. From now on, actually, I'm going to mention these properties, but I'm not going to list them all, because otherwise, as our proofs become more and more advanced, we'll have to list more and more things. So I'm not going to list those things, but you should be able to understand exactly what I'm using. So in this case, it's precisely one of the axioms of ordering. Okay, so if that is true, then I can also multiply both sides of this inequality by the same number. So if I multiply both sides by 1/2, I will have 1/2 t plus radical of 2 is less than 1/2 square root of 2 plus square root of 2. Okay, fine. And then clearly from here, right, I also can see that this is 1/2 times 2 radical of 2, so that is square root of 2. So what we got is that 1/2 times t plus square root of 2, this is going to be less than square root of 2. Okay, so what about something else here? How about if I take this inequality, so I know, so also I know that 0 is less than square root of 2, right? Because square root of 2 is a positive number. So once again, using the properties of ordering, axioms of ordering, 0 plus t is less than square root of 2 plus t, which is the same. If I use commutativity and the properties of 0, this is the same thing as saying t is less than t plus square root of 2. So what we find here, and actually t was is a number greater than 0. So in addition to this would be greater than 0. Well, so what have we got? So then I have this inequality here, and I have this inequality. Actually, let me see if I'm doing what I want to do. No, you know what? Let me change this last. Sorry, I'm going to change this last computation to be the following. So now go back to t less than square root of 2, right? We chose t according to this inequality. So let me do this. Let me now add t to both sides. T plus t is less than square root of 2 plus t. And again, I'm going to multiply both sides by 1/2. So 1/2 t plus t. This is less than 1/2 square root of 2 plus t, right? And this I can simplify again by using the fact that I can use a commutative law. I can interchange square root of 2 and t plus t is 2t, so divided by 2. This will give me t is less than 1/2 t plus square root of 2. Right, so we established two inequalities. One is that 1/2 t plus square root of 2 is less than square root of 2. And on the other hand, 1/2 plus t, 1/2 times t plus square root of 2, this is bigger than t. So the conclusion from this computation is that t is less than 1/2 t plus square root of 2 and less than square root of 2. Well, so let's consider t, only those t that are positive. So if t is positive, so then clearly this guy is positive, so that is positive. And that same number is less than square root of 2. So if t is greater than 0, so t is greater than 0, this would imply that, in fact, t plus square root of 2 divided by 2 is going to be an element of the set S, right? Because this is going to be a number which is greater than t is greater than 0, and at the same time it's a number which is less than square root of 2, so the square of this number must be between t squared, which is 0, and 2. And so that means now that that 1/2 t plus square root of 2, that this must be an element of S. So long story short, actually, it's this is pretty simple. What did I essentially just do? I took square root of 2, I lowered the square root of 2 by a little bit and considered t. Square root of 2 should be a supremum of my set. It should be the least upper bound. So if I go down a little bit from square root of 2, then there should be numbers between t, which is less than square root of 2, and square root of 2 itself. So these numbers must belong to my set of numbers from 0 to square root of 2. What is the easiest number to consider between t and radical of 2, that would be the average, right? So basically what I proved is that the average of t and square root of 2 is an element of S. And not only that, the average of t and square root of 2 should be, by default, bigger than t, because t is less than square root of 2. So what I found is an element of S which is above t, and that proves that square root of 2 is actually the least upper bound. So therefore, 1/2 t plus radical of 2 is an element of S that is larger than t. And so I'm done. Okay, so for the future, again, two things need to be verified to prove that a number is a supremum of a set. And those two things are, number one, that all elements of S are less than this number, and number two, that if I go down from my proposed supremum, then the result must not be an upper bound, so I should be able to find an element of a set which is larger than that number, which is slightly smaller than the proposed supremum. All right, so then in the next lecture, I will consider a couple more examples of suprema and infima, and then we will discuss some relevant theorems.